Hi, Steve Ellingson here. This lecture is about Colpitts oscillators. Here I'm showing a schematic of a Colpitts oscillator. Basically, a Colpitts is any oscillator that happens to have this particular topology where we have two capacitors and an inductor, and they're arranged a certain way. Now, this particular circuit is one of many possible implementations, and it's a pretty good starting point for a whole bunch of options, including fixed frequency oscillators, tuned oscillators, voltage controlled oscillators, and so on. So this is the one I'm going to show, but just keep in mind there's a whole bunch of different ways to implement a Colpitts oscillator, and they're really only different in the details. I'm using a bipolar transistor in the circuit, but again, there's many other possibilities. This could just as easily be a FET transistor, or it could be bipolar or FET in one of the other possible topologies. For example, here it's an emitter follower. It's also possible to implement this in a common base implementation. The tough part about understanding Colpitts oscillators is the fact that the way we draw them as schematics tends to obscure the method of operation. So the first step in trying to understand what's going on here is simply to redraw the circuit. That's what I've done here. So this is the exact same circuit. I've simply rearranged the components to make it easier to understand what's going on. So first, see this block, I refer to it as a gain block, and I give it the identification A. Here I have the resonator, and I refer to this using the identifier B. And so, as in any oscillator, there is a loop, and the loop goes such that the output of A goes to the input of B, and the output of B goes to the input of A, and so on. And that is the basic loop to which the Barkhausen criteria will apply. Two other things in this circuit. First, this little RC circuit is simply for power supply integration, and it's really not essential in this circuit. I include it only for completeness. For details about that, there should be another video. Then finally, there's this capacitor here. It's indicated as a bias blocking capacitor. It's there merely to prevent the DC voltage at the emitter from appearing at the output, which is a friendly thing to do to whatever circuit that is attached to the output here. Okay, so first, the gain block. It's an emitter follower, also known as a common collector configuration. You probably already know that emitter followers are commonly used as voltage buffers, sometimes used as current sources because they have low output impedance. Emitter followers typically have low voltage gain, typically about 1 or so, and in fact, we're going to shoot for that here. We're going to design it to have a gain which is very close to 1. Emitter followers are non-inverting. That means the phase of the output is equal to the phase of the input. So in terms of our description of the blocks here, the phase of A will be about 0. And then also you should know that emitter followers have high input impedance, and we'll take advantage of that. Block B is our resonator. It is an LC resonator, meaning it uses the resonance between inductance and capacitance to create the resonance, and hence the oscillation. The resonant frequency, omega sub naught, is the desired frequency of operation. So this is really all the pieces, right? The resonator makes it possible to oscillate, and the loop consisting of A and B sustain the oscillation. The Barkhausen criteria applies to that loop. The loop gain must be greater than or equal to 1. In principle, it can be 1, but we know that oscillators have the starting problem. Sometimes it's hard to get them to start oscillating, and that's usually helped by making the loop gain greater than 1. So since the gain of the gain block is about 1, we want the gain of the resonator to be greater than 1, and in fact we're going to go for about 2. So the loop gain will be about 2 in our design. And secondly, the second Barkhausen criteria applies to phase. We want the phase to be 0. In other words, we want each turn around this loop to have the same phase, so it reinforces itself. So we want the phase of the resonator block to be equal to 0. Also, I need to emphasize that when I use the terms A and B, I'm referring to the responses of these blocks, and specifically I'm referring to the voltage responses. So A is a voltage gain and B is a voltage gain. Before leaving this page, I want to identify one other thing, the capacitor C3. C3 isn't strictly needed to implement a Colpitts oscillator. That is, not all Colpitts oscillators will have this third capacitor. Here, however, we need it, because if we don't include it, what will happen is that the base will be coupled to ground through that capacitor, and that will short out the base. So if we don't have capacitor C3, then the inductor shorts out the base. So C3 is required, not really for oscillation, but simply to protect the bias. Okay, let's look at the resonance circuit, that is B, first. So what I'm showing here is that block B, drawn out for convenience, extracted from the circuit. The input is over here on the right. That's the emitter terminal on the transistor. And the output is the base terminal on the transistor, shown here on the left. Now remember, we have high impedance looking into the input because A is an emitter follower. And presumably we're going to protect that by selecting resistors R1 and R2 appropriately large. The voltage gain, B, is simply the base voltage divided by the emitter voltage. And one other thing before I continue here, I'm going to take this inductor and expand it in the analysis to include its series resistance, which I've indicated here as R sub L. R sub L, the intrinsic series resistance of that inductor, is usually pretty small. It's expected to be less than or maybe much less than 1 ohm. Nevertheless, it's useful, in fact important to include it here because it does play a role, and so I'm going to drag that along. Next, I'm showing the circuit now rewritten in terms of reactances. So for example, instead of capacitor 1, I'm showing reactance 1. For capacitor 2, I'm showing reactance 2. For capacitor 3, I'm showing reactance 3. And for the inductor, I'm showing a reactance X sub L. And as indicated here, I'm sorry for the clumsy notation, but yes, X sub L is the reactance of inductor L sub 1. Since there's only one inductor in the circuit, that shouldn't cause undue confusion. All right, to determine the relationship between VB and VE, and hence the voltage gain, we just realized that we have a voltage divider here. VB can be written in terms of VE, and here we see one branch in the voltage divider that appears in the numerator, and here in the denominator. And then the other branch in the voltage divider is just this reactance right here. Here we've simply multiplied through by J in the numerator and denominator. And then next I note that since the series resistance of the inductor is very, very small, it should be much less than the reactance of capacitor 3 or the reactance of the inductor. So I can get rid of it, at least for the current analysis, the current part of the analysis, yielding this simpler expression. So now I'm ready to write down what B is, the ratio of V sub B to V sub E. It's simply x3 plus xl over x1 plus x3 plus xl. Note there are no j's here, so the phase of B, the phase of the voltage gain, is equal to 0, and that's what we wanted, as noted earlier. Next, note that at resonance, reactances sum to 0. In particular, if I go around this loop and this thing is in resonance, I expect all the reactances to sum to 0. So that's what I've written here. x1 plus x2 plus x3 plus xl should be 0. And I can use that to write an expression that lets me substitute x3 plus xl for something in terms of x1 and x2. The reason that's useful is because I am interested in B at resonance. That's the frequency I'll be working at. So that lets me replace this with this, and this with this. And now we see we get some cancellation, and we can play with signs. That gives us a simpler expression. B at resonance is just x1 plus x2 over x2. Now I'm going to replace those reactances with their capacitances, work through, do some dividing through, and I have found then that the voltage gain at resonance is just C1 plus C2 over C2. And this is a wonderful result because it means that the voltage gain will be greater than or equal to 1 is required, and this gain is more or less determined by C1 and C2. I say more or less because I've made some approximations already, but to a good approximation, the voltage gain of that resonator is determined by C1 and C2 alone, and so I can fiddle with those two things to adjust the gain, and fiddle with other things to adjust other properties and know that the gain is not affected. So this is a pretty useful finding. Okay, next let's look at the gain block, that is A. First, recall that the emitter voltage gain is given by this expression. In this expression, Gm is the transconductance of the transistor. That's a property of the transistor, and if you've forgotten what that's about, we'll come back to that in just a moment. Z sub L, appearing here, is the impedance looking out of the emitter. So in our circuit, here is the transistor, and here is the emitter terminal. And looking out the emitter, we see the emitter bias resistor. We see C1 and C2. We see C3 and the inductor. And then the high impedance input to the gain block, which again, of course, connects back here. So we don't need to consider anything back to the right here. That's a high Z situation in order to determine Z sub L. So in terms of the schematic, Z sub L is pretty easy to find. It's simply the parallel combination of R sub E and C2 that appears here, and that's in parallel with this branch. And we found earlier that we could rewrite these expressions at resonance. So for example, this much can be replaced with minus X sub 2 at resonance, where we have that special condition that the reactances must sum to 0. So at resonance, this is the load impedance, that is the impedance looking out the emitter. Now we're going to simplify by arbitrarily requiring that the emitter resistor be greater than the magnitude of the reactance of C2, that capacitor right there. Now this is purely to simplify. There's no reason why we have to do this. We're going to do it merely because it simplifies the equations and gives us some nice, simple design and analysis equations to use. You should not forget that we've made this approximation based on this requirement. If we make that assumption, then the impedance looking out the emitter simplifies to this, and we can write this out explicitly as shown here. A little bit of algebra gives us this revised expression. And then finally, we recall that the resistance of the inductor should be much, much less than the reactance of C2, and that allows us to simplify further to this. So to sum up, we have that the impedance looking out the emitter is approximately equal to the reactance of C2 squared divided by R sub L, and that's, of course, using the simplification that we imposed. Now continuing, we're ready to develop an expression for the magnitude of the voltage gain of the gain block. Here is the expression that we wrote down earlier. We can make the substitution for Z sub L and obtain this expression. Now I just want to make a comment here. Looking forward, I'm not going to show this yet, but looking forward, we're going to find out that G sub M, reasonable values of G sub M, expected values of G sub M, will give us magnitudes of this voltage gain about 1. Not merely in the ballpark of 1, but actually pretty close to 1. So I just want to remind you of that now, and I'll show you that that's true later. Given this expression, we can now compute the loop voltage gain at resonance. It's simply the expression we just came up with, multiplied by the voltage gain of the resonator, x1 plus x2 divided by x2, as shown earlier. A little bit of algebra gives us this expression. A little bit more algebra gives us this expression. So that is the loop gain of the resonator at resonance. Now we apply the Barkhausen criterion on gain. That is that the loop gain should be greater than or equal to 1. And to do that, we simply set the expression above equal to 1, multiply through by the denominator, and we get this expression. We note that terms cancel on either side, yielding this very simple result, that transconductance times the reactance of capacitor 1 times the reactance of capacitor 2 should be greater than or equal to the series resistance of the inductor. As promised, the resistance of the inductor turns out to be important here. We need to make sure, in order to maintain that loop gain requirement, that this expression is satisfied. So we're going to need to keep that in mind. Okay, now we're ready to determine the resonant frequency, omega sub naught. So, once again, the starting point is observing that resonance occurs when all those reactances add up to 0. That lets us solve for the required reactance of the inductor at resonance. And now we go back to C's and L's. We obtain this expression, which is solved for omega naught to give us this expression. The expression is seen to consist of two parts. L1 itself, which is clearly the tank inductance, and then this expression, which we can interpret as the tank capacitance. That whole thing has units of capacitance. So this expression is a little bit complicated, and we would like to simplify it. And there's a couple things we can do to simplify. One is we can make C3 large. In other words, we can impose this requirement. We make this approximation, and now the resonant frequency expression simplifies to this. We get rid of one of the capacitance terms. Secondly, we choose C1 equal to C2. Now this is another example of an arbitrary choice intended to simplify. So clearly not necessary. But it has two very nice features. One is that it simplifies the bill of materials. So there are two capacitors that can have the same value. Secondly, it makes the loop gain equal to 2, so that's a pretty good value to start at. The Barkhausen criterion requires the loop gain to be 1. Starting at 2 gives us a little extra oomph for starting. We make that requirement. Now the tuning equation simplifies to this. Simply omega naught 1 over square root of L1C1 divided by 2. Simple enough. Next, the question, what should C1 be? It's really the only thing left that we have to nail down in some form as a component value. And what I suggest here is to observe that C1 appears in parallel with the base emitter junction of the transistor. And you should know that there is a capacitance associated with that base emitter junction. And that capacitance is simply reflecting the distribution of charges that gives us the 0.7 volts or so that appear across that junction when this transistor is operating. Now there's a range of values that could happen here. That base emitter junction could have a capacitance anywhere between a few picofarads up to maybe 20 picofarads or so. But I would say for a typical BJT, you should assume that's on the order of 10 picofarads or so. So here's what I suggest. Make the design independent of the base emitter capacitance by choosing C1, which is appearing in parallel, to be much greater than the base emitter capacitance. Because then the parallel combination of the two, the thing that we actually have in the circuit, is approximately C1. So by making C1 large, we eliminate or at least mitigate the dependence of the design performance on the base emitter junction capacitance. A pretty good starting point for C1, in most cases below 100 megahertz or so, especially using transistors such as the 2N3904, about 100 picofarads or so. Again, maybe 200 picofarads, kind of depends on other things, how you might tweak that. And remember, C1 is one of the two capacitors that determine the loop gain, so that may also be a factor. But in the absence of any information, you probably want to make C1 and C2 100 picofarads to start and then adjust from there. Okay, with all that in mind, let's make sure that the Barkhausen gain criterion is satisfied. We previously derived this equation as a requirement for satisfying that criterion, but we did not actually confirm that that was going to happen. So let's do that now. First, we note that transconductance for a bipolar junction transistor is the ratio of collector current to thermal voltage. And thermal voltage at room temperature is typically about 25 millivolts or so. Collector currents vary, but in most cases we're looking at collector currents that might be somewhere between 1 and 10 milliamps. Maybe sometimes 1, maybe sometimes 5, maybe sometimes 10. In a few cases, maybe slightly lower, slightly higher. But this is a pretty good indication of the range of possibilities. And with that in mind, we see that the transconductance is going to be somewhere between 40 and 400 milliamps per volt. So now if we evaluate this equation at resonance, we get transconductance times the reactance of C1 at the resonant frequency times the reactance of C2 at the resonant frequency. Recall that we're going to try to make C1 and C2 equal, which simplifies this expression. And then finally, let's assume that we're looking at frequencies between 1 and 100 megahertz, and then see what the minimum and maximum values of the expression are going to be. And we find that we expect the result to be somewhere between 10 ohms and 1 megohm or so. And it's pretty unlikely that the value is going to fall outside of that range because we've picked extreme values at each step. Now this is probably okay. It's probably okay because RL, the series resistance of the inductor, is expected to be less than, or probably much less than, 1 ohm. And here we see the lowest value that we expect is 10 ohms. So we're in pretty good shape. One thing to keep in mind though is that the transconductance is a function of temperature, and it's likely that at higher temperatures, the transconductance is going to come down because the thermal voltage will go up. So just keep that in mind. This is always worth checking, and this is a great place to run into problems in practice. So always check your work for the actual circuit you implement under the conditions that's implemented. And if you have problems, this is a great place to check to see if you might be running into trouble. So, what is the gain of our gain block? We came up with this expression for the gain of the gain block at resonance. I think we have all the information we need at this point. X2 is just the reactance of C1 at the resonant frequency. Just to come up with a value that's extreme, or kind of worst case, we'll choose the highest frequency we might consider here. I'm not saying that we can't make oscillators at higher frequencies. I'm just saying for the techniques that we're describing here, 100 megahertz is probably towards the high end of the applicable frequency range. And then we'll choose C1, 100 picofarads, as described later, just for the purpose of coming up with likely values. So here we find that the reactance X2 is minus 16 ohms. So X2 squared is about 253 ohms. So X2 squared divided by RL is either greater than or much greater than 253 ohms. So with that in mind, GM times X squared divided by RL, which appears twice in the gain equation, is either greater than or much greater than 400 milliamps per volt times 253 ohms. That gives us 10 volts per volt. So the voltage gain at resonance, 10 over 1 plus 10, which is very close to 1. And that confirms our previous assumption that the voltage gain of the gain block would be about 1, and we've closed the circle on that. Now we're ready to talk about some biasing considerations. Just a few things to consider. We already constrained or required that the emitter bias resistor, R sub E, was going to be much greater than the magnitude of the reactance of C2. So that's already built in here. Also note that R1 in parallel with R2 has to be large in order to preserve the high input impedance into the emitter follower gain block A. Now, what should you choose for collector current and the voltage on either the collector or the emitter? It really has something to do with the output level of the oscillator, which we haven't talked about. In other words, how many volts peak to peak are we going to get out of this oscillator? Well, I sub C and the voltage on the emitter or the voltage on the collector are certainly going to have something to do with that. It's hard to anticipate what that level is going to be. It's kind of an advanced topic. There's certainly ways to kind of estimate it. But for the purposes of starting here, I would suggest starting with IC in the range 1 to 10 milliamps. If you're absolutely not sure where to start, maybe start with 1 milliamp just to be on the low end. And as often is the case, we could choose V sub E just to be half of the collector voltage, which would give us plenty of swing room for the waveform at the output. When you do this, you can design the bias. Given this much information, you'll get a certain output waveform. If it's too small or too large, you can adjust the output level by changing the bias resistor, R sub E. So that's what I suggest. Start with some value of I sub C, some value of R sub E, see what you get, and then adjust using R sub E, the emitter bias resistor. Of course, there are other ways to do this, other more rigorous and deterministic ways to approach this, but I think in most cases this will get the job done. So finally, some concluding remarks. Just a few things I want to emphasize here about this design. First, we're using a emitter follower gain block which has low output impedance. That does not mean that this circuit can drive a low impedance load. And the reason is because whatever we attach to the output becomes part of the tank circuit. To see that clearly, we can go back to the circuit diagram all the way at the beginning. Whatever I attach out here is actually also connected to the tank. So if I have 50 ohms dangling out here at the output, that 50 ohms is also going to appear in the tank and completely change our analysis. So even though the output impedance of this emitter follower is low Z, you really cannot put a low impedance or a moderate impedance at the output. It really needs to see a high impedance. So my suggestion here is to add to this circuit a buffer. And here I'm just showing it as a generic amplifier. It could be a common emitter transistor amplifier, which certainly is a common design task. All you really need is something that has high Z at its input and is able to deliver the low to moderate Z that you would typically see for the output, like a 50 ohm output. Secondly, I'll note here that we've made a whole bunch of approximations and we've left out a whole bunch of details about the transistor physics. These things that get left out and glossed over, they tend to overestimate the resonant frequency. So in our tuning equation, if we compute the resonant frequency using the implemented value of inductance and the implemented values of capacitors, then we'll typically see the value we actually get is somewhat higher. So don't be surprised if it's even 20% higher or so. What do? You simply adjust L1 and C1 until you get the frequency you want. However, this issue does raise the question of how you can modify easily the frequency of resonance. And a very common way to do this would be simply to add a variable capacitance of some kind to the tank, specifically in parallel with L1. If you do that, then this thing will have a combined reactance which can be tuned, and that can be used to change the resonant frequency. So this particular thing is sometimes known as a Oscillator oscillator. Oscillator oscillators are Colpitts oscillators, they have this additional capacitor dangling out here. Another possibility is you could vary C3, this cap right in here. You can get potentially good results. That's known as a clap oscillator. So clap and Oscillator are just two different variants of the Colpitts basic two capacitor approach that give you some additional ability to tune the tank. That concludes this lecture.